the next session of Strength of Materials. In this session, I am going to solve the 12th question on shear force and bending moment. Calculate the reactions and draw SFD and BMD for the beam loaded as shown in the figure below. In this question, I have taken a UVL, which is a uniformly varying load. So first I'll draw the FBD of this load diagram that is given to me. I'll draw a straight line for the beam. At point A there is a hinge, so I'll write VA. At point B there is a roller, so I'll write VB. Now since this is a triangle, it's a right angle triangle, so the area is half base into height. So this will be 6 kilonewton load, which is to be applied at 1/3 from the end B. So I'll write here this is 6 kilonewton and the distance 1/3 of 6 is going to be 2 meters and this distance will be 4 meter. So this is the FBD. Next I'll go for calculating the value of VA and VB. I'll first do summation of force in y direction is 0. VA is upward minus 6 plus VB is equal to 0. So I have VA plus VB is equal to 6. Next I'll use summation of moment about A is equal to 0 and clockwise direction will be positive. So I have 6 into 4 minus VB into 6 is equal to 0. So I get the value of VB as 4 kilonewton. When I substitute this in equation 1, I'll get VA as 2 kilonewton. So that's a very simple calculation. So I'll write here VB is 4 kilonewton and VA is 2 kilonewton. Next I'll go for the SF calculation. I'll use the sign convention. To the left of section, any force going upward will be positive shear force. At point A, I have to calculate the value of shear force twice. So when I stand at A and I look to the left, there is no value of shear force. So shear force to the left of A is 0. Shear force to the right of A will be 2 kilonewton. When I stand here, I look to the left, I can see VA. Next I'll go to the point B. So shear force to the left of B. When I stand here and I look to the left, I can see 2 upward, 6 downwards. So I'll have 2 minus 6 will be minus 4 kilonewton and shear force to the right of B should be 0. So when I stand here, I have 2 going upward, 6 downward and 4 upwards. So I have 2 minus 6 plus 4, which is 0. So I'm starting with 0 and I'm ending with 0. This check is very important for every numerical that you solve. So I'll just draw the line. This is A. This is SFD in kilonewton. This is B. At left of A, value is 0. Right of A, the value is 2 kilonewton. For left of B, the value is minus 4 kilonewton. And for right of B, the value is 0. Now I have to join these points. If you recollect the table that we had made for UVL, the shear force is going to be a parabolic curve, and for BM bending moment, the curve will be of cubic type. So I'll join left of A, right of A, and this is going to be left of B, right of B. Now for joining this line, first I'll join with the help of a straight line. I've used a pencil, a very light line. Now for drawing the curve, I'm going to trace back to this diagram which is given to me. You can see that this is an increasing type of loading, but if you observe this is actually in the downward direction. So when you have something in the downward direction or you have a negative slope, I am going to draw above the line. So this is a line which I am drawing. This is a 2-degree curve. So this will be positive shear force and this is negative shear force. So I'll join this with a hatching line. So this is my SF diagram. Now you have to understand that here I have got a point which is of 0 shear. Let me call this as point D. Now you can see the diagram labeled till C, so I have taken D over here. I am going to trace back this point D to the main diagram. When I trace back this point over here, you can see I can draw a section. This point is D. Let me call this point as E. Now I want to know the distance of this D from this end A. Let me call this as distance X. For that, over here, I need to know this height ED. So we will start with the calculations. This is the distance X which I want to calculate. For that, I will first use this triangle, and here if you observe, I can say that the two triangles are actually congruent to each other. So I am using, by similarity of triangles, AED and ACB. If you observe here, A is a common angle between the two. D and B both are 90 degrees, so they are congruent to each other. So we are going to have some sides in ratio. So I'll have AD upon AB. I have AD upon AB will be equal to ED upon CB. Now here AD is X, AB is the total distance which is 6, ED I do not know, and CB is 2. So this ED is actually X upon 3. So this is what I obtain, is the value of ED. Now I'll tell you why I'm using this, because I want to calculate this distance X. For that, I have to redraw this diagram, and I'll draw this section A to D, and A to D portion is actually this triangle. So when I use this triangle, I need this height ED. So this is 2 and this height is X by 3 as I've just obtained. So let's redraw this A to D portion. It will look like this. This is D, this is E. You have a UVL here. This will have VA, which is 2 kilonewton. This is point A. I do not know this distance X, and I know this height is X by 3. So when I draw the FBD for this, it will be something like A. Here it will be VA is 2 kilonewton. This is point D. For the area, it will be half base into height. So this will become X square by 6, which I have to place at a distance of X by 3 from this end, and this will be 2X by 3, 1/3 and 2/3. Next, what I'm going to do is, at this point B, I know that the shear force is 0. So here I can solve by saying shear force at D is equal to 0. Let us take up the shear force up to this point. So here I'll see 2 going upward, and I see minus X square by 6 is equal to 0. So here I'll get the value of X as 3.46 meter. So this is the technique which is used for calculating the distance in case the shear force is 0 for a UVL type of loading. So this is 3.46 meters. Now we are going to calculate the bending moment values. To the left of section, I see any moment going clockwise will be positive bending moment. So I start with point A. When I stand at A and I look to left, there is no moment, so it is 0. Next, I'll calculate the bending moment at point B. Again, this should be 0. So when I am at B, VA is turning clockwise and 6 is turning anti-clockwise. So I have 2 into 6, and this will be minus 6 into 2, which is 0. So I start at 0 and I end at 0. Now, you have seen that at point D, which is a point of 0 shear, we know that at this point the bending moment is going to be maximum. So I need to calculate the bending moment at this point. For that I am going to redraw this diagram. So I'll have A to D. At A I have reaction as 2 kilonewton, and this is the point D. Here there is a UVL. This distance I just calculated as 3.46 meter, and this distance is 3.46 upon 3. If you recollect, this height was x by 3. So let's draw the FBD for this. At point A, the reaction is 2 kilonewton. This will be half 3.46 into 3.46 by 3. This is the height, this is the base. So I'll get this value as 2 kilonewton. So this load is 2 kilonewton here, and the distance will be 2 by 3 of 3.46 in meters, and this will be 3.46 by 3, 1/3 distance. So let's solve. I want to calculate the bending moment about the point D. So this 2 will turn with a distance of 3.46, and I'll have this distance as minus 2 into 3.46 upon 3. So I get the answer as 4.62 kilonewton meter. So this is how the bending moment is supposed to be calculated for a point of zero shear for a UVL. Now I am going to plot these values. I have only positive values, so I'll draw the graph a little below. This is my bending moment diagram in kilonewton meter. This is point A and this is point B. At point A the value is 0, at B the value is 0. I'll trace this point down, and here the value is 4.62. So first thing that I'm going to do is I'm going to use a pencil. So I'll just draw a straight line. Now I'm going to observe my SFD again. If you observe the SFD, there is a decreasing curve here, and there is a further decreasing curve here. So I need to draw the curve above the line for both of them. So I'll write down this is a 3rd degree curve, and I'm going to write this is my point D. This is to be joined here. This is positive bending moment, and I'll draw the hatching line. So this is how the problem is supposed to be solved. I hope you have understood the numerical. If you have any doubts, or if you want me to solve any numerical, please write to me in the comment section. Don't forget to like, share and subscribe to my channel. Hit the bell icon for latest updates of my videos. See you in the next session. Thank you.